Hi everyone, and welcome to lesson 20.1. We are going to continue on with what we started talking about in class on page 265 in class today and solving our trigonometric equations. So in class, we talked about graphing the given equation in radians mode and looking at this graph and being able to determine at what point in the year, given our days of the year chart here, that we were able to get 840 minutes of daylight by looking at the intersection in the calculator between our given graph and where it was intersecting at what points, 840. And our calculator was helpful for that, but it was also a little time consuming to do for every single thing we're trying to solve. So that's where solving for algebraic expressions comes in, not using our calculator necessarily. So we want to be able to look at the equation and algebraically solve it as well. So normally we have been focusing on a limit to where our answers can occur for the inverses. And looking around our unit circle where these things could happen, generally we say there's only a specific quadrants that we're looking at, whether that be the restrictions from the calculator or the restrictions that are given, for instance, on the delta math questions where it was 0 to 360 or 0 to 2 pi. Now, officially, we know if we don't restrict domains, though, there's an infinite number of solutions because we go around and around and around the unit circle as many times as we want, because officially they repeat forever if we don't restrict it. So those are called general solutions when we want to understand the fact that if we looked at graphs of sine, cosine, or tangent for infinity, there's an infinite number of solutions possible called the general solutions. So how this works is we would still look over the interval from 0 to 2 pi or 0 to 360 degrees and visualize using our unit circle where these answers are at, but we then will put for radian measures plus or minus or just plus 2 pi k. The book likes plus 2 pi k. I usually say plus or minus. K officially could be positive or negative. That's why they only put plus. But we basically are taking the solutions we were finding prior to this and adding that value to represent the fact that we can keep going around this unit circle for all the coterminal angles an infinite amount of times. Because officially we would have solutions that are coterminal with pi over 4 running around the circle an infinite amount of times clockwise or counterclockwise. Same things with 7 pi over 4 going around the circle clockwise or counterclockwise. We would have all the coterminal values for infinity that are with that. So to look at these, if we're looking at where is sine of x equal to negative 1/2, well, we know on the unit circle that's occurring at 2 spots. Sine is negative 1/2 at 7 pi over 6 and 11 pi over 6. So those would be our two solutions if we were just talking from 0 to 2 pi. But because they want the general solutions, what we would do is we're going to have our final answer then include adding or subtracting 2 pi k, as well as 11 pi over 6 plus or minus 2 pi k. Now with tangent, tangent of x equals the square root of 3 at 2 locations. And with positive, it would be in quadrants 1 and 3, and that's going to occur at pi over 3 and 4 pi over 3, where we're taking square root of 3 over 2 divided by 1/2. So our normal solutions from 0 to 2 pi would just be pi over 3 and 4 pi over 3. But again, because we want those general solutions, we would want to include then the plus or minus 2 pi k factor to each of those. Now, officially though, with tangent, then it repeats more often, right? So you can write this as both of these plus or minus 2 pi k, or we can notice with tangent, it's a little special since it repeats more often. We could also just say pi over 3 plus or minus pi times k, since it's repeating a little bit more often, adding that 1 pi to pi over 3 would also start including 4 pi over 3 and all of 4 pi over 3's coterminal values. So there's two ways you can officially write this answer, since again, we can kind of pick up on that answer with a different piece right here. Now, the next piece of this then is going to look into actually then solving. So notice this equation right here. Imagine we were solving it just with an x, like a linear equation. We would need to solve this, subtract 9, and divide by 4 to get our final answer. That process does not change with trig. We're still going to subtract 9 and divide by 4, but we're isolating cosine of x versus just x. So from there, we need to look then on the unit circle, where are these values occurring? For cosine of x equaling 1/2 from just 0 to 2 pi, we have two answers, pi over 3 and 5 pi over 3 would be our final solutions. Notice they just want the solutions over that interval, not the general solutions. So our other example here looks at using a squared value from 0 to 2 pi. Again, think of it as just solving using x's, not trig. We would take out the greatest common factor between these, which is x, set each piece equal to 0, x equal to 0, and x plus 1 equal to 0. So our two solutions would be 0 and -1. Same idea with trig. Okay, but instead of just factoring out an x, you're factoring out a sine of x. You'll set each piece equal to 0, and then you're going to look on your unit circle, where does sine of x equal 0 and where does sine of x equal -1? Well, sine of x equals 0 at 0 and pi, and sine of x equals -1 at 3 pi over 2. So we officially have three solutions on that interval. So to solve for part A, again, think about this in terms of algebra. What would you have to do first? Well, we would start by moving the 8 cosine of x. We try to isolate that by itself by subtracting the square root of 3 from both sides. Okay, now things get a little tight here work-wise, so you may want to do this in the My Notes section so you have enough room. And we would have, if we subtract 1 square root 3 from 5 square root 3, we now have 4 square root 3's. Divide then by the 8 on both sides to get our cosine of x isolated. We end up with 1/2 square root 3, aka square root of 3 over 2, because the 4 and the 8 simplify. So we're thinking about on the unit circle, where does cosine of x equal square root of 3 over 2? Well, cosine is positive in quadrants 1 and 4, and there are two values at which x is going to be positive square root of 3 over 2, and that's going to be at pi over 6 and 11 pi over 6. The next one is going to be treated like a quadratic. Imagine we rewrote this as just x squared plus 2x equals -1. We would bring that -1 over and we would factor. What multiplies to be 1 and adds to be 2? Well, 1 and 1. So x plus 1 and x plus 1 would be our answers. This does not change at all. The only difference is now these are all tan x's. So 2 tan x here. So it would be tangent of x squared, which we normally would write as tan squared x, and then 2 tan x. So our final answers here really factored are tangent of x plus 1 and tangent of x plus 1. So we're looking, where does tangent of x plus 1 equal 0? Since we have two of the same property, well, tangent of x equals -1 in two locations. Tangent is negative in quadrants 2 and 4 at the values of 3 pi over 4 and 7 pi over 4. Now, there are also some other examples to solve, again, going back to looking at algebra. Now, notice this one is using a secant. Again, think of this like we would be solving our normal algebra problem with just an x. Notice when we take that square root, it became plus or minus. Same thing with the secant squared. Subtract the 2 and take the square root. We're looking where does secant of theta equal plus or minus 2. Now, notice on the right-hand side, you see this left-hand side of your paper on page 268, you see this math tip box. When we're looking for a reciprocal function, since we're not as used to finding those, look at the reciprocal that it's associated with. Secant of plus or minus 2 is the same thing as saying cosine of plus or minus 1/2, reciprocal. So that'll make it easier for us to find. Now, also notice the interval is from 0 to 360 versus 0 to 2 pi. That means we want our answers this time in degrees because those are given, the interval is given in degrees. Okay, and so that's why there are 4 locations that this is happening at between 0 and 360. Thus, we have 4 answers. Okay, so looking at these next examples, again, they're a little tight, so you may want to do these in the My Notes section. For A, B, and C. But as we look here, again, as we start solving, order of operations, add the 1 to both sides and divide by 2 to get sine squared of theta isolated. And then we need to square root. So reminder, when you do this, on the other side here, it becomes plus or minus the square root of 1/2. Now, in order to take the square root, another way that's equivalent to this is looking at the square root of the top versus the square root of the bottom. Square root of 1 is 1, square root of 2 is square root of 2, which is really, after rationalizing, square root of 2 over 2. So essentially what we're doing is we're looking on the unit circle and we're saying at what value is our sign positive or negative square root of 2 over 2 in degrees because it's 0 to 360. Well, that's occurring at 45, 135, 225, and 315 would be your answers there. Oops. And it's officially theta, not x, although they're kind of interchangeable. Sometimes we call our angles theta, sometimes we call them x. The next example deals with a cosecant. We're going to add the 7 to the 5 and eventually then divide by the -6. We're going to look, where does cosecant of theta equal -2? Well, as we talked about up above, instead of using cosecant, let's look at the reciprocal function of sine, since we're better acquainted with that. And the reciprocal of 2 over 1 is 1 over 2. So we're looking on the graph, where does sine equal just -1/2? Well, that's in quadrants 3 and 4 at 210 degrees and 330 degrees. Finally, for example C, we're going to add the 3 to both sides and divide by the 9. We're looking, where does cotangent equal 1 over, cotangent squared equal 1 over 3? Well, again, we're going to need to square root. So we're saying, okay, where does cotangent equal plus or minus square root of 1/3, which is really plus or minus square root of 1 over square root of 3, which after rationalizing, we know is plus or minus square root of 3 over 3. Another way of looking at this, though, in case you don't want to deal with cotangent, since we're better acquainted with tangent, we're looking at where does tangent equal the reciprocal of this, which you might want to look at this piece, just square root of 3. Well, tangent is equal to square root of 3, or cotangent of square root of 3 over 3, at 4 values, because we're talking positive or negative: 60 degrees, 120 degrees, 240 degrees, and 300 degrees. Now, again, if you're not great with your tangents, a reminder, one thing that you can do on this is look at, okay, what's my reference angle? And I know it's in all four quadrants. So you would want to make sure that you looked here and said, okay, if I'm in degrees mode, make sure that happens. I'm not 100% where tangent is square root of 3, but I can look in my calculator to help me out. Oh, 60 degrees. Okay, that's my reference angle, and it's occurring then in all four quadrants associated with the reference angle of 60 degrees. Now, one last thing for today, a reminder, explain why there's officially infinitely many solutions to an equation like sine of x equals 1/2. Well, officially, if we don't restrict sine, it repeats every 2 pi radians. So without restricting sine, it's going to repeat forever and ever and ever and have an infinite number of solutions going through it, which is why we would represent it with that plus or minus 2 pi k, or here as well, 5 pi over 6 plus or minus 2 pi k. Okay, so that's for your general solutions on that. All right, so lots of information going on here, but the biggest thing is understanding the difference between general solutions and then beginning to solve. We will definitely work more with this in class and start looking at that activity 20 worksheet. Thanks for watching.